Hello, everyone. Welcome to today's live broadcast, Next Level PFAS Screening and Identification Using Trapped Ion Mobility Spectrometry. I'm Shannon Stoltz, Senior Editor of Special Projects for LCGC, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by Bruker Scientific. The new Bruker Applied Mass Spectrometry division is focused on the unique needs of the customers or the company's users, with a focus on the food, environmental, forensics, and clinical research and industrial markets. Analytical areas such as characterization, safety, authenticity, adulteration, QC of starting and finished goods are amongst the applications covered and are used across industrial, government, and academic institutes. The Bruker Applied Mass Spectrometry division is dedicated to helping provide complete solutions for the unique needs of end users. So we do have a few important announcements before we begin today. This webcast is designed to be interactive, and we do encourage you to ask questions throughout the event. You can submit your questions by typing them in the Q&A box, which can be found at the bottom of the video player. You can enlarge the slide window by clicking on the small icon in the bottom right corner of the media player, and the slide will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the top right of your presentation window. I would now like to introduce today's speaker. We are very pleased to be joined today by Sam Putnam. Sam Putnam is an application scientist working in the Applied Mass Spectrometry division of Bruker Scientific. He received his PhD in environmental analytical chemistry from the University of South Carolina, researching harmful algal blooms in lakes and reservoirs. He specializes in environmental, food, and forensics applications at Bruker across the company's mass spectrometry portfolio, including triple quad, QTOF, ion mobility, and FTICR instruments. So thank you very much for joining us today. We're very excited for the presentation, and please get us started.
Thank you, everybody, for joining today. We're going to be talking about Bruker's TIMS ion mobility QTOF platform and how that can assist for next-level PFAS screening and identification workflows. So first of all, what are PFAS? PFAS are per- and polyfluoroalkyl substances, which consist of a full or partially fluorinated hydrophobic carbon chain. These are compounds that have been around for a long time. They're very commonly used in a lot of consumer products as water, grease repellents, and heat repellents. And they're really found everywhere: water, soil, food, any sort of materials we may have around. They're highly persistent in the environment, which is where they get the nickname forever chemicals, and this is why they are of such concern to us. There's a lot of evidence that exposure to PFAS may cause adverse health effects, reproduction, development, immune system, may cause tumors. So these are definitely chemicals that we want to be monitoring in the environment and in the products that are around us. What are the challenges of monitoring with PFAS? Well, first of all, they're a huge group of compounds. There are over 4,700 registered PFAS, plus there's degradation products of them, and that number is continuously growing. There's also a lack of reference standards and databases or spectral libraries for a lot of these compounds, which makes it challenging to properly identify them. Also, these compounds are present at a very, very low concentration in some complex matrices, so it's difficult analytically to separate them from the background and from other compounds. Separation and characterization of isomeric PFAS is also important, given that you have long hydrocarbon chains. What those chains can do is be branched or be linear, and this leads to different effects. So it's important to be able to separate these isomers as well. Overall, this leads to a very difficult analytical challenge, but it's an analytical challenge that Bruker's timsTOF Pro 2 and Metaboscape software is ready to take on. So we have a couple advantages with this software and hardware setup. Number one is our VIP HESI source. This is a vacuum insulated probe, heated electrospray source, which gives us very high sensitivity combined with the high resolution for both mass and ion mobility from the timsTOF platform. We also have TIMS, which is trapped ion mobility spectrometry. It's an additional dimension of separation for these complex samples and gives us the ability to identify isomers from each other. Along with ion mobility, we have a CCS value, or a collisional cross-section. This gives us an additional criterion for compound identification for these unknowns. We also have PASSIF, which is our data-dependent acquisition mode for doing MSMS. This gives us maximum MSMS coverage with very high spectral rates of over 100 Hertz for maximum potential to see everything within your sample. We also can do Kendrick mass analysis in our Metaboscape software. This is an excellent filter for PFAS since we can pick out these compounds by their specific CF2 repeat unit, which we'll show more a little bit later in the webinar. We also have the ability to do in silico fragmentation and CCS prediction. This is very important for those compounds that we don't have standards for. Given that there are thousands and thousands of PFAS out there, it would be impossible to maintain a library of all of the standards available to us at all times, and so many of their fragmentation patterns or CCS values may be unknown. That's okay because in Metaboscape, we can predict their fragmentation patterns and predict their mobility values in CCS space using some tools that are built into Metaboscape. So we can take these public suspect lists like the NIST, Norman network that have thousands and thousands of entries and quickly do a standard-free screen with those libraries. So TIMS has a number of advantages when it comes to doing PFAS work. One of those is the separation of isomers. So here we are using PFOS as an example. We do see some separation by UHPLC of these isomers. We get multiple peaks for the same mass there, but we can obviously tell from looking at this chromatogram, there's a little bit more than meets the eye here. We definitely have things co-eluting. In this case, we actually have identified 4 different isomers of PFOS with different degrees of branching. Only this peak all the way here on the right is the linear peak. And the way that we're able to identify these differences is by ion mobility. So in this case, we have a TIMS resolution of on average 135, which gives us these beautifully separated peaks, and we can identify them by their individual CCS values to figure out which one is which. So now we're getting more chemical information from the separation of these isomers, which allows us to understand more about our sample. We also can use TIMS for both separation and quantification of these isomers. When we look at this co-eluting peak here, it would be very difficult to properly quantify this peak given that the valley between the peaks is so small. However, when we move into the mobility space and we start mobility filtering our chromatogram, we can get a much cleaner chromatogram with a peak in it that is representative of only one of the isomers. So by doing this, we are able to actually get different quantitative results for the individual isomers that are present in the sample, again, allowing us to understand more about our sample. We can also use the concept of CCS filtering to clean up our MS-MS spectrum. In this case, we have just the linear PFOS, and by all ion fragmentation, we have quite a busy spectrum here with our mobility filter turned off. But if we start mobility filtering our spectrum so that we only see those peaks that correspond to the mobility of our parent, we get a much, much cleaner spectrum, which can more easily be matched with spectral libraries, and it's easier to interpret manually as well. So this ion mobility can separate these fragments from the matrix. So using this platform of both the TIMS-TOF and our Metaboscape software, we can do both target screening and non-targeted workflows in 2 different pieces of software. Today, we're mostly going to focus on the Metaboscape software, but we do also have our task software, which is targeted analysis, screening, and quantitation. So there are many types of analysis that we can do with these. Specifically with task, we can do known unknown screenings, retrospective screenings, and suspect screening for a more targeted workflow or a workflow that needs accurate quantitation. For our unknown identification and some suspect screening as well, we can do that in our Metaboscape software. So both of these softwares do have some overlap, and we have great software solutions for both a quantitative analysis as well as this non-targeted analysis. So first, let's talk about what does the task screening and quantitation workflow look like. Well, step 1 is we generate a high-resolution extracted ion chromatogram trace for our principal ions. We know what our targets are for task, and so we've programmed those into the software. We're able to pull out that extracted ion chromatogram. The next step is to do peak detection and retention time check. In this case, we've actually pulled out 2 different peaks that are coming out at 2 different retention times. We want to make sure we select the correct peak that aligns with our known retention time. After that, we do verification via diagnostic ions. These can be different isotopic peaks, various adducts that may be formed, such as the M+ sodium peak, as well as fragments that come from our broadband CID or data-independent acquisition. All of these factors combine together to give us a scoring that's based on mass accuracy, retention time, our isotopic pattern, which we call sigma, and diagnostic qualifier ions. This gives us a very easy to use traffic light score where we can quickly look at our ions and identify what is a good match and what might need some manual review. Of course, after we've identified our ions and compounds, we can then move into quantitation within the software as well, doing all of our calibrations, normalizations, internal standards automatically as part of that software workflow. What this looks like for a traffic light score means that we get a very, very easy to use piece of software where we can quickly identify where we need to focus our time as an analytical chemist in order to understand those results better. By looking at this column, we see that those that have all green results are a good match. So in this case, we have a compound confirmed on accurate mass, retention time, millisigma, and qualifier ions. All 4 of those are good. And of course, we can also have a CCS value match in here as well when we're on our TIMS platform. However, we have another fragment in here where we may need manual review. We see that for our qualifier ions, we have a yellow, which means that we may want to review this because it's not meeting the guidelines that we've set out in our method. We can also look, of course, at our chromatograms and mass spectrum in order to get an in-depth data review. And so what this really does is simplify the process of targeted analysis so that we're only spending time on those samples which need our individual attention. Moving into Metaboscape for our non-targeted or screening workflow, the step 1 there is our acquisition of our LC passive data. So passive is our data-dependent acquisition MSMS mode that we can run at speeds of up to 100 Hertz, giving us unparalleled MSMS coverage. Once we've acquired that data, we extract features from that data, combining our isotopes and adducts, including our mass and mobility calibrations, retention time alignment, and MSMS import, using our Metaboscape software and our T-Rex algorithm. Once we have those features in our software, we then want to screen for knowns or suspects using something like the NIST PFAS suspect list, which has almost 5,000 entries, as well as any other smaller target lists we may have, for example, one using the EPA targets from 533 or 537. Once we've screened for our knowns or suspect compounds, we can move on to identifying unknowns using our various annotation tools within Metaboscape, which we'll go over more here in this slideshow presentation, as well as live with the software. Our Kendrick mass filtering and statistics can be done at any step in this process to help us identify which individual features, whether they're known or unknown, are most important to our analyses. What is contributing to the differences between samples, or for example, which ones are the most intense in one versus another. Using TIMS and Metaboscape, we analyzed 2 different water samples. One is an original drinking water sample, and one is spiked with a PFAS mixture. These samples were provided by the University of Amsterdam to us. The data processing in Metaboscape revealed over 1,300 features in this case, and of those 1,300 features, greater than 95% of them had MSMS coverage. This is the power of passive, and running at 100 Hertz rates, we are able to really get a very good coverage with MSMS data on almost every feature that we're collecting. We can then filter this data with Kendrick mass analysis. The way that we do this is we define the repeat mass unit of CF2 as 50 mass units here, and then our Kendrick mass defect is the nominal Kendrick mass versus the exact Kendrick mass. What this allows is homologous species aligning horizontally. So our y-axis here is going to be our Kendrick mass defect. And what we will see is that if we have samples that have a similar repeat unit, in this case CF2, they're going to have Kendrick mass defects that are very, very close to 0. That means that PFAS, in this case, because we have a CF2 repeat unit, are going to align very close to this 0 axis, whereas other compounds that might be present are going to be far away from them. This gives us a quick filter so that we can understand where the PFAS are in our sample and select these features individually and ignore the other features in our sample that may not be as important to us. We can also see distinctions between different types of PFAS as well. In this case, we can see different lines where different types of N group chains are aligning with each other based on their unique Kendrick mass defect. So this is what a plot looks like in reality from our water sample. So in this case, we're plotting, again, that CF2 versus M over Z. And so this separates our PFAS from the other features that are there. Even though we have, I believe it was upwards of 1,300 features, we can see that the features that are important to us if we're focusing on PFAS are down in the bottom part of this plot. Selecting just this area of potential PFAS features, we have now narrowed our scope to 118 features from well over 1,300. What this allows us to do is focus in on the features that matter most to us and not waste our time identifying things that may just be present in the background or at low concentrations that we're not concerned with. In this case, PFOS is right here on this mass plot. So this allows data reduction by more than 90%, which decreases the amount of work that we need to put in manually. So as a proof of principle, we use two different target lists here, with 25 PFAS coming from the EPA method 533. Both of these target lists contain the molecular formula here, so we have a name and molecular formula in our list. But what we did is we used one of them as we would traditionally think about a targeted analysis, where we put in specific retention times, we have a CCS value that's been measured for these, and we can assign them to a MSMS library spectrum. However, we also have theoretical information like INCHI structures. This allows us to predict in silico fragments and CCS values using our CCS Predict Pro algorithm. So we don't necessarily need this experimental data like retention time and CCS value. We can just use the structure string that we have here and predict those things. So this is exactly what we did, and we used both of these target lists, one with actual experimental data and one with just theoretical data, in order to better understand how this will work within Metaboscape. So within Metaboscape, we annotate with our target list using various scoring parameters where we can adjust the quality of the matches with things like accurate mass accuracy, retention time, millisigma, MSMS scores from that library matching, as well as a CCS value for ion mobility matching. This is all done on the fly with in silico fragmentation prediction using MetFrag and CCS values using CCS Predict Pro. So you don't need either of these experimental pieces of data. We can let the software predict those for us. Again, we're going to get this annotation quality score, which we have seen also in our task software, but here as well, which will tell us, compared to, in this case, the predicted MSMS values, what are we looking at, or the predicted CCS values? How well do those match with those predictions? So for example, we're going to select one compound. And here we see we have a retention time, an accurate mass, a CCS value. This will be for every feature. And in this case, we've matched it using this name and formula. And what we see here are the mass error in ppm, in millidalton, and also a millisigma value, which indicates the goodness of isotopic pattern fit. We also will look at these in silico fragments that are calculated from the structure, and we can see that we have 83% intensity coverage across 3 fragments. The software will also try to identify what the structures of these fragments are so that we can take a look at them and using our chemical knowledge, see if these fragments make sense. So continuing, we also predict our CCS value. We didn't know what the experimental value is here, but the predicted value is within 3.4% of our actual measured value. Typically, we see a result below 5% for a predicted value match. So this, again, tells us that we maybe have the correct confirmation here for that compound. So the scoring of the final result, we can see that we have mass accuracy. We don't have retention time deviation because we don't know the retention time, but that's okay because we also have criteria like millisigma, the MSMS score from in silico fragmentation, as well as that CCS value showing us what the match is there. So all of these tools are built in within Metaboscape in order to give us the best possible match. And what we found here from this proof of principle is that the target list using the experimental data with that retention time and CCS value, and the target list that only had theoretical information with that value calculated on the fly, gave us very, very similar results. So what this tells us is we can do standard free screening. We don't necessarily need these retention times and experimental CCS values because we can predict MSMS spectra and those CCS values. So this gives us a very, very powerful tool given that these target lists are providing equal results and allows us to do things like use the NIST suspect screening list in order to screen for thousands and thousands of PFAS all at once within the sample. We also see that we're identifying isomers with this technique. So with the INCHI-based suspect list, we can see that we have multiple features, all with the same name, same formula, but we can see that these are coming through at slightly different retention times, and more importantly, different CCS values. In some cases, these retention times may be so close together that we may not be able to fully chromatographically separate them, but on a timsTOF, we get a CCS value for each one of these, which can be matched with the predictions here, which we're seeing good matches with the predicted CCS values, helping us to further confirm these compounds. So using this NIST PFAS suspect list, the exact number is 4,967 compounds, so just shy of 5,000. This data has been aggregated from public sources, publications, patent websites, EPA comp talks. So it's just a really, really big database of all of these names, formula, and then structure keys. So our results here using this was that we identified PFAS in both of these water samples, and we found an additional 67 features using the NIST PFAS suspect list. 46 of them were from our spiked compounds, so we knew those were there. We wanted to make sure we could confirm them by this technique. We also identified 5 different isomers in there, and we also got 8 additional annotations from the NIST PFAS suspect list. These 8 features were identified as actual in-source fragmentation fragments of carboxylic acid, so losing that CO2 fragment. And we were able to do this using feature correlation plot within Metaboscape to try and identify these features that are correlated to each other and have very, very close retention times, which is a good indication of in-source CID fragments. We also identified PFAS in the 2 water samples using the t-test. So one of these water samples was plain water and one was spiked. So we know already that they're going to be different, but this is a good example of how these statistics tools within Metaboscape can help us identify differences in samples. So out of the 46 spiked features, we see that in this volcano plot here, only 13 of them are showing a significantly higher intensity in the spiked sample, which means that most of the PFAS are already present in our non-spiked sample. So this can quickly identify differences for us between various samples. If we look here, the intensity plot for this specific compound shows that although we are detecting it in the spiked sample, it's also present at a pretty decent concentration in the original sample. So this is not contributing as much to the differences between the samples, given that it is already present in the original sample. The additional 8 unexpected compounds we have in here are actually belonging to low abundance signals that are present in both samples. So we're able to look at very, very low intensity signals and using our non-targeted screen, pick those out. One other thing we wanted to show is homologous PFAS displayed in the Kendrick mass plot. So in this case, these are our perfluoroalkyl sulfonic acids, and we can see they're perfectly aligned in a row with each other. So this will show us those different types of PFAS compounds we might have. And we also see some of the fluorotelomere sulfonic acids that are grouped in this line slightly below them. So in summary, TIMS enables the detection of PFAS isomers in complex matrices, and PASIF with 100 Hz MSMS gives us far superior coverage in order to really dig deep into our data. The Kendrick mass defect analysis that we can do within Metaboscape allows us to separate PFAS from other non-fluorinated compounds, allowing us to focus in on a data reduction of about 90% in this case, that allows us to look specifically at the compounds we're interested in. Using a list such as the NIST PFAS suspect list with nearly 5,000 entries, with those molecular formulas and structure keys, allows the use of accurate mass, isotopic ratios, in silico fragments, and predicted CCS values with real-life samples in order to get good identification, and we showed that that matched very well using a more traditional experimental target list. And lastly, we have statistical tools within Metaboscape as well, such as PCA, t-test, hierarchical clustering, PLS, and this allows for comparison of samples or to a reference between a blank, a spiked sample, anything like that, to be able to go through and identify how the samples are different, what features are different between them, and what features may be important to us. We also have some additional reading here with application notes, flash notes, and technical notes that are also available from Bruker for a little bit more information about how we do our PFAS analysis. And with that, I'm going to end the presentation slideshow part of the webinar, and we're actually going to move over into Metaboscape to show you how some of the things that we've done in our PowerPoint here are done in real time and how easy it is to perform within the software. Okay, so now that we've seen some of the things that Metaboscape can do, what I want to do is go through the software and demonstrate how we can get all of those results and how easy it is to process and annotate our data. So I have already processed some feature tables, which we'll look at in a moment, but let's go through the process of how we would add a feature table and get our data processing. So I'm going to go to this LCGC PFAS webinar project that we have here, and I'm going to create a new feature table under this experiment. So the feature table is the core of Metaboscape, and the first thing we need to do is process that feature table. So I will name this feature table demo. This is a negative polarity data, and this was collected on our TIMS instrument. So we're going to be using our T-Rex 4D workflow, which incorporates ion mobility into the algorithms. The next thing we need to do is add our actual data. So for that, we will go select this folder that has our 6 data samples in here. And then we will assign these analyses to their respective samples. These are already here because I have already run these tables with these samples, but you can create as many different samples as you'd like, indicate to the software whether this is a sample, a quality control sample, or a blank, as well as group these together. So I'll drag these over as well. And we can see that these are separated by sample type, so this is the group that I have here. We can define additional groups if we would like to, and have as many groups and attributes as we'd like. So in this case, we have a spiked sample and just a plain water sample. The next step is to select how we will be doing our recursive feature extraction. So the first slider controls how many features must be found in order to trigger the recursive feature extraction. In this case, I'm going to set it to 2. So a feature must be found in at least 2 of the 6 analyses to trigger the recursive feature extraction. Once we've triggered it, that feature must be present in a minimum number of now 3 analyses for it to show up on our feature table. We're actually going to use one more, even more restrictive filter on this, and we're going to filter features by occurrences in groups. So we have our group sample type, and we're actually going to require that we find the feature in 100% of the samples that are in that group. These samples are replicates of each other, so we are only interested in features that are actually going to show up every single time that we run this sample, and this allows us to ignore any features that may come from just noise or some sort of a contaminant that was in one of the injections. The next step is to go through all of our processing methods and calibration methods. So you can have multiple different methods saved in here. There is full version tracking for any of these methods. I've already created this PFAS method for our 4D processing, so let's go ahead and have a look at that. What we're doing in this method is setting things like an intensity threshold, how many points must be across the 4D peak in order for it to count as a valid feature, whether we're using intensity or area for that feature signal, and then some other things like a retention time range, a mass range, so we can limit where the algorithms are actually looking for features, as well as importing our MSMS data. We also have to tell the software what types of ions we're going to be looking for. In this case, we are going to load up this method here, where we are looking at a possible seed ion of an M+ chlorine, as well as a common ion of a water loss. So we want the software to look for both of those. You can add additional seed ions. For example, if you're in positive mode, you may want to add sodium and potassium adducts as well, or if you have a common loss, a neutral loss like a water loss, you can put that in here as well so that the software knows to look for those ions. And then the last step in here is going to be our automatic recalibration. In this case, we're going to automatically recalibrate every sample for mass. So the reason we're going to do this is because we want the most accurate mass data possible for every single individual sample. So the way that we run our data here at Bruker is that every single sample will have a loop injection of calibrant at the beginning, and we want the software to automatically pick up that retention time segment of calibrant and automatically mass calibrate our data. This can also be done for mobility calibration as well if you have ion mobility calibrants in that initial segment. We also have the option of using internal standards in here. This particular analysis does not have any internal standards in it, but that's an option in the processing of the data as well. Here we have annotation methods. So if we're doing a more routine analysis where we already know what methods we're going to be using to annotate our data, we can have the software automatically do this as part of the processing. In this case, I'm actually going to uncheck these because we're going to walk through all these different annotation methods and steps live in person as we go through and show you what all those annotations are. So I'm going to go ahead and click Finish. So what you'll see happening is we have processing happening in the background here. All of our samples have loaded, and this feature table is now going to process. So in the meantime, I'll open up a feature table that I've already processed in the past, this one right here. This will take about 2 to 3 minutes to process for this number of samples and this number of features. So just in the interest of time, I'm going to skip ahead to one that's already been processed, but we can see this going on in the background live. What we have here is a feature table that we see has a result of 1,038 features. This is about the correct amount for this type of a sample. We want to use some knowledge about our sample to determine, is this the correct number of features? Is that too low? Is it too high? For example, if I had something like a wastewater sample, I may want to see more like 5, 6, 7,000 features. Or if I had a very simple sample, like for example a tablet dissolved in some water, that may have only a few hundred features. So in this case, 1,038 features is a pretty good number for this data set. So we're going to go ahead and open this feature table. We can actually see the processing in the background. We're already at 52% on the feature table that we processed, so that does go pretty quickly. So what we see now is the main Metaboscape layout, and at the heart of Metaboscape is the feature table. Currently, we've done no additional annotation or processing on this feature table, so what we have is just a list of all of the features that are in our sample, and you can see for each individual feature in here, we have a retention time, a CCS value, a measured M over Z, and then a list of what ions we found with it. In this case, it was just M minus H, and we also have an indicator whether or not we got MSMS data for that particular feature. So currently, this is a pretty blank table in that we just have a long list of features, and none of these are actually corresponding to any compounds yet. We also have a couple graphs up here, which I'll go into a little bit later, and we can see our individual samples as well and select specific injections as opposed to an entire group. We can see that red and green over here are the spiked and non-spiked samples, and for any feature we click on, we can see their intensities between the different samples and see if there's any difference there. This will become much more important when we get into actual identified compounds. So the next step, once we have this feature table, is we want to annotate the feature table. And we have several different annotation tools that we can use in Metaboscape. These are organized in this list somewhat in the order that I typically use them. So starting with a target list, which we saw before, this is how we do a targeted analysis with compounds that we already know the formula or structure of. We can also annotate with spectral library. Metaboscape does support several different spectral library formats that we can match with, and smart formula as well. Smart formula is our tool for finding the molecular formula of these features. So I'm going to go through this in order and start with the target list since that's the easiest and most simple type of annotation to do. So if we go to Manage Target List here, we can see that this target list that I have pulled up right now has about 70 compounds in it. A target list can contain just a name and a molecular formula, but you can also add things like a retention time, a CCS value, a linking to a spectral library so that there's an MSMS spectrum linked with it for spectral library matching. We can also have INCHI structure keys, and now in the newest version of Metaboscape, SMILES is also supported. So this target list can be very comprehensive. In this case, this target list that we have here is just a list of names, formulas, and then the structure key in here. So this is how you would do a standard-free screening where we don't know any of the retention times or necessarily CCS values, but we can still enter those structures into this target list and then leverage things like in silico fragmentation and CCS prediction in order to get better matching. We also have a version of a target list that includes retention time and CCS values. So this is one that we created for this method. In this case, we have 28 compounds, and we can see for each of these there is now a retention time and a CCS value, which means that we can now match on those criteria as well. So the first step is going to be to annotate with our target list. We can actually annotate with multiple target lists at once. So I actually have 3 PFAS target lists here, one that includes the retention time and CCS value, one that just includes the name, formula, and structure key, and that's from EPA 533. And then we have another list that I believe has 70 compounds on it. So we can actually use all of these target lists at once, and we can search them either in parallel or hierarchically, depending on the ranked importance of these target lists. In this case, I'm going to search them in order, starting with that one that has retention time in it. Again, we have another method that has full version tracking, so we can keep track of this target list method that we're using to annotate We are going to do it on the whole feature table, and over here we have a bunch of tolerances and scorings that we can use in order to judge the quality of this data. So I'm going to click Start here, and this will run through our feature table and annotate on all 3 of those target lists that I have in there. Most of our annotation processes are very fast. The longest step for processing time will always be creation of that feature table, which, depending on the number of samples you have and the complexity, could take anywhere from 1 minute to maybe about 15 to 30 minutes. In this case, our target list annotation is going pretty quickly through here. All right, almost done. And it's going to ask me if I want to save changes, which I do. And so now we have processed our feature table. So if I sort now in my feature table by annotations, we can see that the target list has now identified lots of these features. So now, in addition to our retention time, CCS value, and M/Z, which we had before, we now have a name and a molecular formula. It tells us where we found this annotation from, which target list it came from, as well as a little traffic light indicator of our annotation quality. So we can look at things over here like the exact mass matching. So this is the difference in M/Z in millidaltons. We can also see millisigma values, which is isotopic pattern matching. And for those that match to a compound with a retention time, we can see that this one, for example, has a delta retention time of 0.01 minutes. So very, very close there. So we now have a lot more criteria that we can use to judge these samples. We can also start identifying which ones of these features are actually important to us. Obviously, anything that's on this target list, we have a specific target for, and so we want to make sure we're paying attention to these features. We can start looking into them to see what are their differences in the samples. Are there any differences between the spiked and non-spiked samples, which we do start to see here. Obviously, one of these is spiked, so it will have higher concentrations for those compounds which we spiked into it. All right, so now we've done target list, but that's a targeted method, and Metaboscape is a non-targeted software. So let's move more into the non-targeted annotations that we can do. The next one coming up is going to be spectral library. So next thing we'll do is annotate with our spectral library, and I have a spectral library annotation method I've made for this with all of our PFAS libraries. Bruker has a variety of different libraries that are available. One of them is the NIST 2020 MSMS library. We also have Metabobase and the HMDB Metabolite library. In this case, that NIST library and actually this in silico library, which I got from MS-DIAL, is also going to be the most useful to us. So sometimes we have these more proprietary libraries. We also have things like MassBank, which are open source libraries. So we can search this as well, and much like the target list method, this has tolerances and scorings, what part of it we're going to do it on. So we're going to run this as well, so that we will now have target list annotations and spectral library annotations. So one individual feature within Metaboscape can have multiple annotations on it. Sometimes those annotations will agree, sometimes they will disagree, and that's something that we can search for in our annotations column here in order to see if we're getting the same result from a target list identification and a spectral library identification. So again, we're doing this on our entire feature table of about 1,000 features. And so what we found here is, if I resort my annotations, we found that we do get some spectral library matches. So for example, let's just look at one of these. If we hover over our annotations here, we can see that we match to the in silico MSMS library, as well as our target list that has the name, formula, and structure key. So now looking over here, we have an MSMS score. This MSMS score is out of 1,000, where 1,000 would be a perfect match. In this case, we have a 727 match. That's because this spectral library we're using here is in silico, so there are no intensities associated with these peaks, just the exact mass values. So usually the MSMS scores are a little bit lower. We see that the target list and spectral library identifications are actually separate from each other here, which means that the software thinks it found two different identifications for this. So let's move into our compound ID section to see if this is actually the case. So what's happened here is we have a target list annotation, PFHPA, which is perfluoroheptanoic acid, and we see that the spectral library looks different. While these have the same formula, the reason that these are matching differently is because this is actually just a different name. The target list is using the abbreviation, the spectral library is using the name, but we can see that they've identified the same molecular formula there. and we can see our MSMS spectrum here, or we could go ahead and look at our MSMS library search and compare our query spectrum with our spectral library match. Like I mentioned, in silico library, so we don't have intensities for these, but we do see that this 168 fragment is matching up between them. So that's where our matching comes from for that spectral library result. So now our feature table has more information in it. We have target list as well as spectral library matching. So what's the next step? We still have several features in here which maybe did not match at all to a spectral library or target list. Well, we still want to maybe identify these features, find out more information about them. So the next step will be to run smart formula. So I'll go to my smart formula annotation tool. And in this case, because I'm interested in PFAS and not so much in all of the non-PFAS compounds, I'm going to run a series of parameters in smart formula that are specifically designed for PFAS samples. So for example, I am telling the software that it must find at least 5 fluorines. Now these settings are obviously not good for compounds that are not within that PFAS family, so we may get some poor identifications on non-PFAS, but mostly what we're interested in here are the actual PFAS samples. So I'm going to run this on my feature table next. And what this is going to do is look at the exact mass data, the isotopic pattern, as well as some of the MSMS data in order to determine what the software thinks is the most likely molecular formula. Now obviously for some of these there may be hundreds of possibilities, so we do need to use a little bit of our own chemical knowledge to figure out if one of those formulas is correct or not. So smart formula has now finished, and you see we now have an SF annotation. So for most of these where we have a target list, we can see that the target list and smart formula are coming up with the same result. If we go to our compound ID page here and look at our results, we can see that smart formula has given us this molecular formula here, which matches perfectly with our target list and our spectral library formula, so we can see that that is a good match. We'll also see that for all of these compounds before that did not previously have any kind of annotation on them, we now have smart formula. So for a lot of these, we were able to come up with a formula. We could be more restrictive on our scoring tolerances in order to maybe eliminate some of these that may not be real formula, but we do have a lot of options now. And in fact, we have to scroll pretty far down our feature table before we get into compounds that did not have a formula. So right now we have smart formula on about 317 of these features. That number can be much, much higher if we went with a more general smart formula parameter. In general, what we're looking at right now are PFAS compounds only. The software won't be able to find a compound based on the limits that we've put in for anything that is not a PFAS. Okay, so we now have a pretty good amount of annotations on our feature table. So obviously anything that's on that target list, we can feel pretty confident, particularly if we have a retention time associated with that. We can feel pretty confident that that's the correct compound. But there's some other things that we can do to either simplify or look through our data a little bit more. So the next thing I'm going to point out, which again comes from the PowerPoint, is how you would do a Kendrick mass defect analysis. So built right into Metaboscape up here at the top, we have a various number of plots, one of which is the Kendrick mass plot. So what we can do is set our Kendrick mass defect repeat unit to CF2, which is in here. So we're essentially looking for compounds that have that repeat unit of CF2, and those compounds will align along an axis of 0 on this Kendrick mass defect plot. So once we do that, we see that we're actually separating out a large amount of our compounds. Everything that does not have this CF2 repeat unit is going to be clustered up here, whereas all of our PFAS-like compounds that do have that CF2 are aligning in an axis down here. So what this allows us to do is actually select just these compounds that we suspect of being PFAS. These graphs are fully interactive, so I can actually just click and drag a box around all of these compounds, and this will select all of them in the feature table. So if we scroll up and down our feature table, we can see that there's multiple different things selected in here. So what I'm going to do is label these in our feature table, right-click on them, and say that I want to flag these, and we'll use a blue flag here. Now what I've done is put a flag next to all of these features that are of interest to me, and I can actually narrow down my feature table by that flag color. So we will filter by flag, and we'll type in blue. So now we're only looking at features that have that blue flag, and we can see our plot has updated up here, where we only have this Kendrick mass plot where everything's aligned along 0, and now we're down to approximately 85 features. So this is one of the big powerful tools within Metaboscape, is that we can use statistical tools, Kendrick mass defect, to limit down the scope of the actual features that we need to look at. We can also use statistic tools in Metaboscape, one of which is our t-test. In this case, we have two different samples. One of them is spiked, and one of them is not spiked. So this is a perfect situation in which to run a t-test. So if I go here and click New t-test, we can choose, let me just set this to missing value substitution as the group mean. And now we will click OK. And this generates a volcano plot for us. So we can see which compounds in here are leading towards differences between the samples. In this case, we know the samples are different because we spiked one of them and one of them is not spiked, and we can identify which specific features are causing those differences. For example, right here, perfluorotridecanoic acid, this is leading to a very large difference between the samples, because if we look at our intensities, we can see that this is very much found in the spiked sample. This is one of the compounds we spiked in, but it's not so present in the regular background water. So in order to do this, we can, again, click and drag on these features and maybe just select those features that are most interesting to us. So there's a lot of statistics tools, plots, and various other techniques that you can use within Metaboscape in order to simplify the workflow. The last thing I want to show here in Metaboscape is a little bit of an example of what if you don't have any annotations. Maybe all you have is smart formula, so you have a supposed formula here, but you want to identify what that compound is. As an example, let's again go to this perfluorotridecanoic acid, and let's just pretend that we did not identify this compound. So I'm going to delete all of the annotations from here. And so now we have a compound that has no annotations on it. So let's walk through the compound identification workflow here. So if I go to compound ID, the first step is I can look at my extracted ion chromatogram and mobilogram. These both look like this is a real feature, right? This is definitely present in our sample. We can see there's a clear difference between red and green here. That's the spiked and non-spiked. So now we can go into our Smart Formula tab, where again we have the list of elements and lower and upper formulas that come from our PFAS-specific settings. And in this case, we're also using intensity coverage from our MSMS data in order to find the best result. So here we have our top formula here, which is our C13HF25O2. This is in fact the correct formula. So our Smart Formula settings have done a good job here giving us the correct formula, but we can choose this best candidate here and then move on and move through our compound ID workflow. So the first option is to just say, use this for the annotation. We will then have a Smart Formula annotation. We don't currently know what compound this is, so maybe I'll just say suspect, but we now have an annotation for just that Smart Formula here. But let's get a little bit further into it. Let's now use Compound Crawler. So what Compound Crawler does is takes the molecular formula that we identified from Smart Formula and searches a variety of databases. In this case, we got results from PubChem, ChemSpider, and then AnalyteDB is whatever may be contained within spectral libraries or target lists within Metaboscape. So we can see we're coming up with perfluorotridecanoic acid, which we know is correct. So we could find, just by looking through a couple of these, we can look at the structures and say, oh yes, this is the correct identification, and we could stop here, use this for our annotation. Now we have an actual name. It's pulled in that PubChem identifier as well, and we can click OK. We now have that annotation. But let's say we were in a situation where maybe all of these results look good to us. We do have a couple interesting structures in here. So what we can do next is let's take all of these results and then put them into in silico fragmentation. So we have MetFrag built right into Metaboscape so that we can quickly move from our compound identification workflow into in silico fragmentation. What we see here is we now have a ranking of results based on scores. We can see that all of these are ranked exactly the same because they're all giving us the same structure, which we know is the correct one. These are just slightly different versions. In this case, we actually have the fragments are the same, but we have a little bit of branching going on here. So we can look at some of these as well. So now we know that we can eliminate some of these other options because they do not have good in silico fragmentation matching results. Again, we could go right here, use this for our annotation, and now we have a MetFrag annotation. But we can go one step further because this is a TIMS TOF instrument. maybe we see that all of these have the exact same results from in silico fragmentation. In fact, some of them are exactly the same, but we do have this branch structure here, which is different than some of the other ones. So let's take this branch structure as well as the linear structure and put both of them into our CCS predict function. So we have this one and this branched one. We're going to go back to compound crawler. So we're going to take this one and the branched one. We're going to right click and say predict CCS values. This will ask us which model we want to use. We have a model specific for lipidomics and then CCS Predict Pro, which is a general use model. So we're going to use that one. And then this takes us over to CCS Predict. In this case, we can see predicted values for both of them. So for the linear one, we have a measured value of 196, a predicted value of 200. And so we can see that this is an error of about 2.5%, which is pretty solid for a predicted value compared to a measured. For the branched, again, we have 196 with a prediction of 200. So in this case, there's not enough branching that the predicted values are very different. In this case, they're actually 0.4 square angstroms apart. So we can't necessarily determine whether this is branched or linear based on CCS value, but this does help us confirm that we probably have the correct structure because this CCS predicted value is so close to the actual measured value. So again, we can use now this for our annotation as well. So because we've collected annotations from all these different steps of the process, when we go back to our results, we see that we now have multiple different annotations on here. In fact, probably the METFRAG or the CCS Predict annotation would be of the highest quality since that has sort of the most steps to it. So this is now the one that's using is this last one, CCS Predict. And when we go back to our overview table, we can see that we now have annotations on this compound for CCS Predict as well as all of the other ones that we did in there, and it shows that we did this manually on there. So really overall, Metaboscape gives you a lot of tools for identifying which features are important to you and then walking through the process of identifying those features and turning a feature into an actual molecular confirmation. And so with that, I will end here and take any questions you may have.
Awesome. Thank you so much for that informative presentation. So quickly before we get started on the Q&A session, I would like to remind our audience how to submit questions. You can submit your questions by typing them in the Q&A box, which can be found directly below the video player. So our first question today is, does using ion mobility affect the sensitivity of the instrument?
Sure, great question. So in the sense of a negative effect, no, it does not. In fact, we can actually improve the sensitivity in some circumstances because we're actually able to separate out some of these peaks from a noisy background. We can actually improve sensitivity, not because of any sort of signal count, but because we're able to remove a lot of that noise. So in some situations, we actually get a benefit.
Great, thank you. So another great audience question that came in, can you add DART to this application to eliminate chromatography?
Sure. So DART is fully enabled with some of these workflows that we have. Usually the way that we would use DART in this sort of a situation is as more of a screening technique. So for example, if we have some known samples and we want to quickly go through a lot of these samples with relatively minimal sample prep and time, we can go through and screen for some PFAS in there. And then maybe for the ones that come up positive, we can do a further confirmation by LCMS. Certainly for some of the non-targeted work we can do on DART if we have higher concentration samples, but we still use LCMS as well for doing some of that more non-targeted exploratory work.
Great, thank you. And how would you identify PFAS that do not have an available standard?
Right, so this is one of the things that Metaboscape really lets us do. So the workflow for that would be to find the formula and name as well as the structure key for this. So even though we don't have an actual standard, we can put that structure into Metaboscape and then use some of the tools that we just saw like CCS Predict and METFRAG based on that structure to try and determine some matches, even though we don't have an actual empirical data for them.
Thank you. And what kind of isomers can be separated with a TIMS TOF?
Sure. So generally what we're separating with isomers, specifically when we talk about PFAS, we'll be looking at a lot of branching versus linear. So a lot of PFAS are, long chains, And so we can get different degrees of branching. So we're not just seeing, for example, 2 peaks. We might be seeing 3, 4, 5 peaks for the different degrees of branching. Generally, we're looking for pretty significant structure changes in there that cause a very large difference in collisional cross-section. So the only things that we really can't do are maybe positional isomers, where we go from like ortho para meta, but otherwise we can tell apart very, very small differences, sometimes as small as 2 square angstroms in CCS value. So there's a lot of different isomers that we can look at.
Great, thank you. And are the library searches being conducted with in-house static libraries, or is it searching web-based data on the fly?
Sure. So the MSMS spectral library, those are in-house static libraries. You can also pull in libraries from other sources as well. As far as matching with compound crawler, where we're searching for the molecular formula, that is done live with an online database. So as those databases update, that is a live web-based search.
Thank you. And this next question coming in is from someone using an Orbitrap system for their research. The question is, how does TIMS TOF compare to Orbitrap in terms of PFAS separation?
Sure. So Orbitrap is going to usually have a little bit higher resolution. So from a mass resolution perspective, that will be a little bit different. However, there's no ion mobility stage on an Orbitrap. So the big advantage you would get with PFAS is being able to distinguish different isomers from each other, as well as being able to clean up the background a little bit more by that mobility separation. We can pull out distinctive MSMS spectra, and chromatograms that are a little bit better filtered. So I think the big difference there would be just sort of a complexity reduction and trying to eliminate some of that matrix noise.
Great. Thank you so much for both answering those questions and for your presentation. With that, it does look like it's already time to wrap up. So I'd like to thank the audience for attending and participating in today's event. And I would also like to thank our sponsor, Bruker Scientific, for making today's educational webcast possible. We would like to ask everyone in the audience to participate in a brief survey that will appear on your screen after today's presentation has ended. You'll also receive an email alerting you when this webcast will be available for replay, and we invite you to forward that announcement to your colleagues who may have missed today's live event. We hope to see you all next time. Thank you and goodbye.